Good day, everybody, and we are back again together. And we are still looking at that paper from the Mpumalanga province that was written during the prelims, the recent prelims. So, yeah, welcome back. And for those of you that haven't subscribed, please join our channel and become, part of the family. All right, and by the way, for those of you who still need assistance with mathematics or physical science, please don't hesitate to just give us a shout, and our email address is info@mlungisinkosi.co.za. All right, so today we're going to look at question 6, and this is based on the Doppler effect. I like these questions that have to do with graphs because remember, we need to also, work on our skills on how to, synthesize knowledge and so on. All right, so let's get into it. They say we've got a boat that is moving towards a stationary listener. Okay, the siren of the boat emits a sound with a frequency of 800 hertz. So in this case, I want you to note the frequency of the siren of the boat is 800 hertz, right? But they said, but the listener detects a different frequency, of course, in this case, due to the Doppler effect, right? Now, they say take the speed of sound in air as 335 meters per second. Remember, that is not the speed of the, of the source or the listener, but it is rather the speed of sound. All right, so the first question they ask us, they say, name the phenomenon that was observed by the listener. Note in this case that that phenomenon is the Doppler effect. Okay, right, now they say, how will the frequency that the listener detects compare with the frequency of the siren of the boat? Choose from higher than, lower than, or equal to. So remember that the boat was moving towards the stationary listener. Okay, so obviously it means that those sound waves would be compressed, okay, towards the listener. And so as a result, the listener, or in this case, the detector, will actually hear a higher frequency. So our answer there should be higher than. Okay, so that's 6.1.2. So remember we said on 6.1.1, okay, sorry about that. So on 6.1.1, that should be, we said that's the Doppler effect. Keep that in mind. Okay, so that's our answer to that. And on 6.1.2, we said, okay, that will be higher than. Okay, and in this case, it's because those sound waves, of course, they didn't ask us to explain, but remember, it's because those sound waves are more compressed when we move towards the listener. Okay, so that's higher than. And now for our 6.1.3 answer, they said if the boat is moving at 20 meters per second, okay, calculate the frequency that is detected by the listener. Okay, so what we're simply going to do is just use the Doppler effect equation. So frequency of the listener, V plus minus VL, okay, V plus minus VS times Fs. Now, in this case, what are we looking for? Right, we want to calculate the detected frequency, but remember that they told us that the listener is stationary. So in this case, it means that I'm going to have VL as 0. So in this case, we're going to have V. Now, remember, for those of you who haven't watched our video on the Doppler effect, please do yourself a favor and do that, and you'll see what we are talking about here. So in this case, I've got V and Vs here. Now remember, I want my answer. I already know what to anticipate, right? I know that the answer should be greater in this case, right? So the frequency of the listener should be higher than that of the source. So in order for it to be higher than that of the source, it means this fraction here must be an improper fraction. Remember, whenever you multiply by an improper fraction, so for instance, an improper fraction would be 3 over 2, something like that. The numerator must be greater than the denominator. So if I want that denominator to be smaller, Will I use a plus or a minus? And of course, you know that it should be a minus, okay? So in this case, it would make this guy smaller so that this guy, this fraction would be an improper fraction, okay? So multiplied by the frequency of the source. Now let's substitute. So we said the speed of sound is 335. So that's 335 divided by 335 minus, remember the speed of the boat. They said it's 20 meters per second. Okay. And this is multiplied by the frequency of the source, which was 800 hertz. Okay. And that should give us, okay, I get an answer of 850.79 hertz. And of course, as I said, we already anticipated that the frequency of the detected sound waves should be higher than that which is emitted by the source. All right, so let's move on to that graph question. All right, so they say during an experiment, a learner moves towards a stationary ambulance. Okay, I'm just going to move this. Okay, so they say a learner moves towards a stationary ambulance. Okay, the learner registers the detected frequency of the ambulance siren and the following equation to draw the graph below. All right, so I want you to please note, first of all, they actually rearrange the equation in that way. And I want you to notice on the graph, they actually have FL, frequency of the listener, over frequency of the source, as the y-axis, on the y-axis, as well as the velocity of the listener on the x-axis, right? Now, they made it in such a way that even when they give the equation, that this becomes, the equation of a straight line in a sense. Now remember, in this case, the equation of a straight line, and I want you to think about it, okay? Right, we'll get to the analysis of this, but in this case, the graph of a straight line is always y is equals to mx plus c, right? Now note, in this case, y is always on the y-axis, but in this case, note that our y is FL over Fs. So it means that this is going to be the y. So this is FL over Fs. That's what's on the y. And then m, this is the coefficient of x, right? Now note that our x in this case is VL. So I want you to look at that equation there. So you've got VL divided by V plus 1. So this is kind of your mx and this is your c value. Now look, if we're going to rearrange it, look at this. So it means this is our y, this is going to be FL over Fs, okay, which is going to be equal to, now I'm going to rearrange this in such a way that we've got our x, which is VL. So it means you've got 1 over V, all right, multiplied by VL plus 1. So what represents your m? What represents your gradient there is actually 1 over V. Can you see that? Okay, so it means that this is y is equals to mx plus c. All right, so let's have a look at the questions that they ask us. They say use the equation above to write down, note they didn't say calculate, to write down the quantity represented by the gradient. You see we got that there. So what is represented by the gradient? Okay, you can see the gradient represent the inverse of the speed of sound, isn't it? Okay, so that's 1 over V there. And then they say calculate the speed of sound. You see what they want you to do. So you already know that the gradient of the graphs represents the inverse of the speed of sound, and they want you to calculate the speed of sound. So in fact, what we're going to do is then we have to get the gradient underneath this graph. Okay, so let's do that. Let's calculate the gradient, and we know that gradient is always going to be change in y divided by change in x, or in this case it's going to be the change in FL over FS, okay, divided by the change in our VL values. So let's take our y values. Okay, let's try and pick a value. So I'm going to take this as my x1 and y1 value. So it means that my VL value there is 0. Yeah, that's going to be 0 and 1. So let's pick another value over there. Okay, let's take this one there. Now, I want you to note, how do the divisions actually increase? Remember, these are the major lines in between there, the more solid lines. And in between them, you've got about 10 lines. And I can see this is between 1 and 1,05. Okay, so it means if there are 10 lines in between there, you'll say 0,1,05 minus 1, which is 0,05. So it means each line, each division there has an increment of 0,05, which means two of them increment with 0,1. So if you think about it, if I take 2, it's 1,1, another 2, 1,2, another 2, 1,3, another 2, 1,04 rather, and another 2, which is 1,05. So can you see that? So this will be 1,01. Okay, that's 2 of them. 1,02, another 2, and 1,03, 1,04, and 1,05. Now I'm going to take this value here at 10. So it's going to be VL is 10, and VFL over FS, I think this is going to be 1.01 there, 1.02, 1.03, 1. Yeah, I think this is 1.04. Nope. So that's 1, 2. Okay, yeah, this is 1.03, definitely. Okay, so I'm going to calculate that gradient and say y2 is 1.03. So that's 1.03 minus y1, which is that 1 there. Okay, over, now remember, I started at 1,03, which is this value. What is my V value over there? That's 10, okay, divided by, okay, what was our, subtract rather, what was our X value or our VL value over there? That should be 0, okay? So this is when VL was 0, okay? Right, now that we've got that, can I just remove that so that I can continue calculating on the other side? Okay, so in this case, now that I can calculate that gradient, okay, I've got 1.03, okay, minus 1, which is 0.03, divided by 10, okay, and I get a value of 0.003. So it means that my gradient is 0.03. But remember, what does gradient represent? Gradient represents 1 over the speed of sound, isn't it? Okay, and they wanted us to calculate the speed of sound. So it means that, okay, we know that m is equal to 1 over v, and we want the speed of sound. We know that m is 0.03, okay, which is I think this was 0.003. Sorry about that. 0.003. I got that incorrect there. 0.003. Okay, So in this case, what am I going to do? I'm going to say this is 1 over v, but if I want to get the speed of sound, which is v, okay, so I've inverted this, so it means I need to also take the inverse of 0.003. And what do you get for that? 0.003. I'm going to take the inverse of that, and I get 333.33. 333.33. And remember, we're talking speed there, which is in meters per second. Okay, sorry about that. All right, so I hope that makes sense. And essentially, we've got ourselves our full marks. That was out of 10 marks, and there it is. We are done. Doppler effect, done. Okay, so I hope that you understood that question and you enjoyed it. All right, for those of you who wrote this paper in Mpumalanga, I hope you got this one correct. All right, otherwise, I'll see you guys again next time. All right, sharp, sharp.